Okay, I'm back. So the alternating series test. So each of the terms an are positive. So we have a sequence of positive numbers. Each one is positive. The sequence is decreasing eventually. So the n plus first term is smaller than the nth term. In other words, the terms of the sequence are going down. And we require that the limit of the sequence be 0. So the terms are shrinking to 0. If we have all three of these conditions, then we can be sure that the alternating series converges. Whether it doesn't matter if it's the first kind or the second kind, whether the first term is negative or the first term is positive, it converges. What's basically happening here is you're starting with like a term, and then you're adding a term, so you're moving to the right. But then you're subtracting a term that's a little less, so you're moving to the left but not as much. And then you're moving to the right but not as much because the next term is smaller. And you keep on moving back and forth. You're oscillating about a limit, and it turns out that a limit must exist. So it can be proven that there has to be some kind of limit there, L. That's basically the idea of why it works. All right. I think we're ready to just go right into an example or so. Let's start with a simple example. So you can try to pause right here. I'll read the problem to you and maybe explain a little bit, and then you can try it yourself. So using the alternating series test, prove that the alternating harmonic series converges. All right, that's the problem. Prove that the alternating harmonic series converges. You have to satisfy the three conditions for the alternating series test. All right, so let's take a look. So identify the sequence an. So the series has the form -1 to the n plus 1 a sub n. So this is the negative sign, right? The oscillating minus sign. Sometimes it's positive, sometimes it's negative, depending on the value of n. Right? If n plus 1 is even, then -1 to an even power is 1. So this is responsible for the oscillation. Okay, so the actual sequence that generates the alternating series is a sub n is 1 over n. Clearly, it's positive. Okay, we found it. It's positive. Good. Next, let's check that it's decreasing. Monotonicity means decreasing. Well, we don't really have to check this, right? As n gets bigger, 1 over n gets smaller. That's clear because n plus 1 is bigger than n. So, right, n plus 1 is always bigger than n. So 1 over n plus 1 is always smaller than 1 over n. So as you go farther into the sequence, the terms of the sequence do decrease. They did something a little fancy here, which we'll actually look at later on in another section. Ratios. They did the ratio of the n plus 1 to the nth term, and they divided them, and then they realized that n over n plus 1 is always less than 1. You could also use calculus and take the derivative of 1 over x, and its derivative is negative. So once again, the function 1 over n is obviously decreasing. We know that already. Okay, so we got that. So next we want to apply the alternating series test. All right, so let's just double check that the limit as n goes to infinity of 1 over n is 0. Yes, that's easy. We know that already. So all three conditions are satisfied by the alternating series test. That's theorem 2. So we know that the series converges at the very least. Does it converge absolutely? No, because if you take the absolute value of every term, you would get back to the harmonic series. And we already know that it diverges. We could use the integral test if we forgot, or the p-test, p equals 1. But here's the work for the integral test. Not required. You could just quote, this is a p series, p equals 1, diverges. So it does diverge without the absolute values. Conclusion, the series converges conditionally. In fact, it converges by the alternating series test to the natural log of 2. All right, so let me show you something neat. I could do this on the computer here. I utilized AI to write some Python programs that can show you how infinite series converges. I could do these myself without AI. They're not hard, but it was very convenient to just have AI do them in 5 seconds. I definitely couldn't do it as quickly. So the geometric series 1 over 2 to the n, where the first term is 1/2 and the ratio is 1/2. So we know the answer to the nth partial sum, and we know that the infinite series converges to a over 1 minus r. So you don't have to worry about this code. You'll learn about this next year when you take Python programming, but this is a Python function here. A lot of this stuff is just comments, which means it's just there to help us understand what's going on. All right, so if we run this code, I'll show you what it looks like if you run it. So this is the first 10 terms of the infinite series. See here the 1/2, 1 over 1/1/2 squared, 1/2 quantity cubed, right? 1/2 quantity to the 4th power. So these are the terms that we want to add up, and this is the running sum. These are the partial sums. Some of the first 2 terms, some of the first 3 terms, 4 terms, some of the first 10 terms. So if I would like to do this for more terms, like let's say 50 terms. So here are the first 50 terms. As you can see, it's already rounding. It's already rounding the answer. I think I could give it more decimals here. Let's say 12 maybe. You can have it display more decimals right here. That's the thing about using AI encoding. You have to know a certain amount. Otherwise, you'll have no idea what the computer is doing. You won't be able to understand it. So if you know a little bit of coding, the AI could really augment your skills. All right, so as you can see, it's getting closer and closer to 1. It's not exactly 1. There would be a lot more decimals to notice that. All right, so these in the alternating series. So here are alternating series. This is the one that we just did, the alternating harmonic series, -1 to the n plus 1, starting from the term n equals 1. So this is the code for it. See, this means exponent here. The double star, that means exponent. And this is how you do a running sum. All right, 100,000 terms. We're not going to list out 100,000 terms, obviously, but it'll calculate them. And it just did, and it's very fast, as you can see. In fact, Python is actually, this looks fast. You want to see how long it took. 0.075 seconds. So that might seem fast to you, but it's actually very slow compared to most other computer languages. Like C++ is a lot faster. All right, but it did it, and 100,000 terms, it got 693142. We actually know the answer to this series from theoretical math. It's the first 6 digits should be 693147. And another interesting series is the odd terms. Imagine the odd terms of the harmonic series. I showed it to you on the previous page. So that's actually supposed to converge to pi over 4. And you could see if you do 100,000 terms, it's 785,396, and it should be 785,398. So this is actually a very poor way to calculate pi. It's like the worst possible way. There are infinite series that converge much faster. Literally 10 terms would give you 10 digits or something along those lines. So this required 100,000 terms to get barely to get 6 digits, right? All right. So just to show you, and here I plotted the convergence. I used AI to do this. AI is particularly good at putting in this tedious stuff of plots and making plots view and things like that. So here's the partial sums bouncing around. Unhelpfully, it connected these dots. It might have been better to just leave these as dots here, but it tried to connect the dots. All right, so hope you enjoyed that little Python tutorial. All right, so let's see what else we have. All right, it's really the same work that we just did for -1 over n squared to the n plus 1 power there. So, and remember, if you were to write this out, just to make sure you all understand, when n is 1, that's an even power. N plus 1 is even, right? So it's 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus 1 over 5 squared, and so on forever. This is the alternating p series, p equals 2 series. So once again, the generating sequence is 1 over n squared. It's obviously positive, and it decreases. You could use calculus if you like. 1 over x squared, x to the minus 2, take its derivative, -2 over x cubed. When you cube a positive number, it's positive, and the negative sign makes it negative. So it is a decreasing function, as we already know. You know the graph of 1 over x squared, right? It just looks like this when x is positive. All right, and of course the limit is 0. We know that it heads to 0. We know the limit of 1 over n squared is 0 as n goes infinity. Right, pretty easy. Okay, so by the alternating series test, the alternating series converges, right? The alternating series up here converges. This series converges. This is equal to that. That series converges. And does it converge absolutely? Well, take away the negative signs and just make every term positive. And yes, this is a p equals 2. We already know the p equals 2 series converges, p greater than 1. If you really love the integral test, you could do it again, do the improper integral, and there you go. You see it actually converges by the integral test. So the conclusion here is that this series converges absolutely. Okay? To tell you the truth, if you're a good infinite series student, you could have skipped all of the alternating series stuff here and gone right to here and said this converges absolutely by p equals 2, so it must converge conditionally too. It must converge as a regular alternating series. In other words, it was unnecessary to use the alternating series test because the absolute convergence is a lot stronger. It implies that the alternating series test will work. But the purpose of this problem was to get some practice using the alternating series test. So just keep that in mind. That's why we did that. All right. here's another similar example. -1 to the n over the natural log of n. The natural log of n is positive if n is greater than 2. The natural log of n increases, so 1 over the natural log of n must decrease. Okay? If you want to check it with a derivative, I don't know if I would recommend doing it like this, but you can. If you just know that the natural log graph goes up like this, see if you memorize the graph of the natural log graph, you know that it's a straight increasing function. So if you take its reciprocal, it has to decrease. The 1 over an increasing function is a decreasing function. But as you can see here, that's positive, x is positive, a negative, it's always negative. So yes, it is a decreasing function. In fact, if you really have trouble seeing it, you could use your calculator. 1 over natural log of 2, 1 over natural log of 3, 1 over natural log of 4. See, you can see it's decreasing. The limit, once again, you need to know that the limit is of the natural log is infinity, and then you could easily see that 1 over the natural log goes to 0. Okay, so once we have that, the alternating series test will work, and we know that the series converges. However, this series diverges. Absolutely. The series diverges absolutely. This next part is a little bit probably difficult because this integral looks like it might not be the easiest integral to do. 1 over the natural log of x. So this is probably a little bit more advanced than we are going to be used to. So I wouldn't ask you like a complicated integral like this, but if you're interested in how to do it, I would actually do a comparison test here. 1 over n is actually smaller than 1 over natural log of n. Right? Think about that. N is a lot bigger than the natural log of n. Always remember that. N is much bigger than the natural log of n. The natural log of n is the exponent that you need to recreate n. So 1 over n must be smaller than 1 over natural log of n. So by the comparison test, this series must diverge because that series diverges. The harmonic series diverges. All right, so the conclusion here is that the series converges conditionally. All right, so I invite you to look at example 4 on your own. It's a similar problem. I wanted to show you a little bit about, let's look at one that does not satisfy the alternating series test. This is important, a divergence problem. So why don't I give you a couple minutes, why don't you pause the video, try to do the alternating series test on this particular infinite alternating series. Give it a try. You could pause the video for a minute. Notice what goes wrong. The n over n plus 1 does not converge to 0. In fact, it converges to 1. So if you go all the way down here to step 4, or maybe right here, if you list out the terms of the sequence, like with your calculator, you'll see that the series, the sequence does not converge to 0. So by the divergence test, we know that the series cannot converge, because a series only converges if the terms go to 0. You can't add up infinitely many terms, even with a alternating negative signs, unless the terms go to 0, and that does not. So it does not satisfy the alternating series test, and it fails by the divergence test. So the divergence test proves that the infinite series cannot converge. It's basically oscillating between plus and minus 1, right? When n gets big, n over n plus 1 is basically 1. So it's like you add 1, subtract 1, add 1, subtract 1. Doing that forever leads to divergence. Here's an interesting series. This is actually the series for e to the minus 1. It actually converges extremely fast because of this n factorial. N factorial is even bigger than exponential. So that really decays fast. And in fact, we'll learn this later when we learn about power series and Taylor series. We'll learn how to prove that this is actually equal to e to the minus 1 power. That this series is actually e to the minus 1. And it converges absolutely. So I invite you to try out example 6 on your own. Let's move on to the last thing I want to show you is the error estimate and remainder bound. All right, so this is a little complicated, so pay attention carefully here. Alternating series remainder. If S is the infinite alternating series and it satisfies the conditions of the alternating series test, and S sub n is the nth partial sum, then the remainder S minus S sub n satisfies this bound. Okay, so what does this mean? What it means is S sub n is the sum of the first n terms. Big S here is the sum of all the terms. So the remainder would be the difference between all infinitely many terms and the first n terms. It's called a tail of the series. So for example, if you want to see what a tail would look like, so let's say this is our series. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. This would be S sub 6, the sixth partial sum. The sum of the first 6 terms, right? Now we know that there's a lot more terms, right? 1 over 7 minus 1 over 8 plus 1 over 9 minus 1 over 10, and I'll put dots here. So these terms here, there's infinitely many of them. This is a tail. This is called the nth remainder, r sub n. So it's the infinite tail of the series, the right tail. The tail, well, there's only one direction going to the right. So all these terms together, that is the error. That's what we're off by. See, all the terms together, that's the exact sum. That's S. So there's 3 things going on. There's S, which is the sum of the infinite series, all the terms. There's S6, which is the sum of the first 6 terms. And then there's, so I guess this would be R6. Sorry about that. This would be R6. That would be the remainder, the remaining terms in the infinite series. And what we hope is that R6 is small, and in fact, the alternating series error theorem tells us that the absolute value of the remainder has to be less than or equal to the 7th term. See, that's an n plus 1 there. So it has to be smaller than the 7th term. All right, so what is the 7th term? Well, the 7th term is 1 over 7. That's the positive one, right? If you want to be safe, you could just put an absolute value here, but it's not necessary. So what that tells us is the error is smaller than 1 over 7. That's how good of an approximation you get if you only use the first 6 terms. 1 over 7 is more than, it's like 13 or 14%, right? So there's like a 14% error. Maybe not percent error. 0.14 would be your error. All right, so let's look at one example here. All right, so use the alternating series test to approximate the natural log of 2 with error less than 0.01. How many terms do we need to use to make sure that we're off by 2 decimals or less? You know, we want our answer to be accurate to approximately 2 decimals, right? Okay, so this is the alternating infinite series we're interested in. The remainder, the error, is less than the n plus 1th term, which is 1 over n plus 1. So we basically want 1 over n plus 1 to be less than 0.01. Solving for n is greater than or equal to 100. It's technically greater than 99, but that's a strictly greater, so we want it to be greater than or equal to 100. Whether you give the answer as 99 or 100, it's fine. Either one is okay with me. Okay, so what does that tell us? So what that tells us is if we add up the first 100 terms, we're guaranteed that our error is less than 0.0099. What is the actual error? The real answer is the natural log of 2, which is right here. So our predicted error is 0.0099. The actual error is about 1/2 of that, 0.0497. So indeed, our theoretical estimate for the error is sound. In other words, if you're doing some kind of problem, engineering problem, and you need the answer to be an infinite series calculation, well, this kind of idea will tell you that you need to use the first 100 terms of the infinite series to get an answer of the desired accuracy. Very, very important concept. All right, so let's stop here. I'll make a little homework set for you guys to try, and hopefully I'll see everybody on Wednesday.